Hi everyone, and welcome to my physics tutorial video. I'm going to teach you about what the Lorentz force is, how to calculate for the Lorentz force, and how to use the right-hand rule to know which direction the force is acting on the particle. So to start off, we need to know what the Lorentz force is. And the Lorentz force is the magnetic force on a charged particle that is moving through a magnetic field. What we're going to start with is obviously the equation. So the Lorentz force can be represented as F equals Q V B sine theta, and these all stand for different variables. The Q stands for the charge of the particle. This is important because the Lorentz force can only be calculated if the particle has a charge. If there is no charge, there is no Lorentz force. The next thing that we see is the V is equal to the speed, or velocity. And then B is the magnetic field strength, which is the unit of that is the Tesla, and that's based off of an inventor whose last name was Tesla. And then the theta is just the angle between the directions V and B. So we're going to jump into our first practice problem using the Lorentz force equation. So if we have a particle with a charge of 3.4 times 10 to the negative 19th coulombs, it moves upward at a speed of 10 meters per second. If the magnetic field strength is, what is the magnitude of the Lorentz force on the particle? So here we have this particle, and it's moving upwards between these two magnets, which are creating the magnetic field. So if we look at this, we're going to do red because I like red. So if we see these things, so we have 3.4 times 10 to the negative 19th as the charge. I'm just going to write E in here. And then our speed is 10 meters per second. And then our magnetic field strength is 1.7 Teslas. All right, and if you go through and do the math and you do 3.4 times 10 to the negative 19th times 10 times 1.7 times the sine of 90, you get 5.78 times 10 to the negative 18th. So this means that our particle that is going through this magnetic field here is feeling a force of 5.78 times 10 to the negative 18th newtons. So the next one that we're going to do is a little different. So this one, it says a 3.6 times 10 to the negative 17th coulomb charged particle is moving at 7 meters per second through a magnetic field. If the particle feels a force of 9.8 times 10 to the negative 15th newtons, what is the strength of the magnetic field? So here we're using the equation that is usually solved for force, and we've rearranged it to be solved for the magnetic field strength. And so for this one, we're going to put in, so if newtons is on top, we have 9.8 times 10 to the negative 15th. Don't mind my writing. And then coulombs are 3.6 times 10 to the negative 17th. And then our meters per second is 7. And if you go through and do the calculations on this one, we're going to get a magnetic field strength of 38.89. Of course, I'm rounding. Alrighty, then we're going to move on to some practice problems after we discuss the right-hand rule. So the right-hand rule gives us the direction of the Lorentz force. And this is important because the numbers we were calculating beforehand were the magnitude of the Lorentz force, but they weren't telling us which direction that particle was being pushed. So in these diagrams that I've drawn, we have the red line representing the magnetic field, which was the variable b beforehand, and then green is the velocity of the charged particle. That's the direction it was originally moving in, and the blue one is what direction the Lorentz force is going. And so if you stick out your hand and you have your thumb pointing to the right and your pointer finger pointing away from you, and then you stick your middle finger up, this is the gesture that your hand is going to be making whenever you are using the right hand rule. So if we scroll down, we can start with some practice problems. So in this first one, we have our magnetic field is going to the right and our velocity is going up. So if you hand and you stick your thumb up and then you have your pointer finger pointed to the right, then what you do is you have your middle finger pointing out in the same orientation so that the gesture looks the same. And you'll see that the Lorentz force is pushing outwards, away from you, but technically into your screen. So this one, the force is going into the screen. And then for this one, we have our particles moving towards the right, so that's where your thumb is pointing, and then the magnetic field is pointing upwards. So then if you stick your middle finger out, it would be going towards you, which is another name for out of the screen. So these are just two examples of how this can be used when trying to find the direction of a particle or something that is being changed by the Lorentz force. So these are some more practice problems that I wanted to do. This first one says into the screen because this represents a magnetic field line that's going away from you and into the screen. And then this one says out of the screen because this is a representation for magnetic field lines that are coming towards you and out of the screen. And these are just some things that you'll have to get used to seeing when doing direction things that occur with the Lorentz force. And so for this one, we're going to start. We have our thumb pointing down in that same direction as that green line that represents the velocity of the particle. And then we have our pointer finger pointing away from us and into the screen, which means that our middle finger is pointing out and towards our right. And then for the second one here, we're going to have our thumb pointing to the left, and then our pointer finger pointing towards us. And then we're going to have our middle finger pointing straight up because that's how the hand gesture looks. And so this last one I want to go over is kind of tricky because if you try and put your thumb to the right and then your pointer finger to the left, unless your hand is really flexible, it's not going to work. And so from that we know that there would be no Lorentz force on that particle if it's moving in that direction. This is also kind of interesting because the equation that we were using before showed us that F is equal to Q VB sine of theta, right? But in this, we know that theta is the difference between V and B, and here it's 180 degrees. And the sine of 180 degrees is 0, which is why the force would be 0. And I am done. So I hope that you guys learned a lot about the Lorentz force.